Section 3.3, Development of Quantum Theory. So particles and waves, they behave very differently on a macroscopic scale. So, we can observe waves, we can clearly observe particles, but however, on a microscopic scale, there is really no clear separation between particles and waves. So previously, in the two prior sections, I briefly mentioned how light, it has what's called, it acts as both a particle and a wave. So this is called wave-particle duality. Light acts like a wave, as we see with c equals lambda nu. Light has a wavelength, it has a frequency, but light also can act as a particle. It exists in the form of photons. So this is kind of an interesting dichotomy here, that light is both at the same time. And actually, when you get down to a small enough scale, matter is the same thing. There is no clear separation between particles and waves, so matter itself can be seen as both a particle and as a wave. So what's interesting here is we can actually calculate the wavelength that matter has. This is called the de Broglie wavelength, and so this is calculated using this equation here. Again, this equation will be on the reference sheet. You don't need to memorize it, you just need to know how to use it, and a little more importantly here, you need to understand what the variables are. So lambda, as always, is wavelength. H, once again, is Planck's constant. Mass, or m, represents mass, and here u represents velocity. So m is mass in kilograms, and u is velocity in meters per second. So you can use this equation to calculate the wavelength of matter. Let's look at an example. What is the de Broglie wavelength of a 25-gram bullet traveling at 612 meters per second, where h equals 6.626 times 10 to the negative 34th kilograms meters squared over seconds? And here, Planck's constant just has slightly different units, because this will help the units cancel out. It's still technically joules per second. We just took joules per second. We took the joules and the joules seconds and broke it down further to make these units a little more specific. That way they will cancel out successfully, just to leave us wavelength. All right, so first, you're going to want to convert grams to kilograms, because remember, when you use the de Broglie wavelength equation, the mass has to be in kilograms, and your other clue there is that Planck's constant has the unit kilograms, so your mass value better have the unit kilograms as well. So convert grams into kilograms. So 25 grams, convert that to kilograms, you get 0.025 kilograms. Now you can plug everything in, because the velocity is already in meters per second. So h is Planck's constant, plug that in up top. M is mass in kilograms, plug that in, and u is velocity in meters per second. So you plug these values in, you calculate and solve, and you get 4.3 times 10 to the negative 35th meters. So the de Broglie wavelength of that bullet is 4.3 times 10 to the negative 35th meters. So that bullet does have a wavelength. That wavelength is just so spectacularly small that we would never be able to observe it on the macroscopic scale. That's why, to our eyes, matter simply just behaves as particles. We don't notice the wave aspects of matter, because their waves have such a small wavelengths. But if we zoomed into a small enough scale, we would begin to notice these wavelengths. All right, let's do a knowledge check question. What is the de Broglie mass of a photon of light with a wavelength of 366 nanometers and moving at a velocity of 8.55 meters per second? All right, the correct answer here is C, 2.12 times 10 to the negative 25th grams. So your equation is lambda equals h over m times u. Now you're solving for mass, so I'm going to rearrange this equation to solve for mass, and you get h over lambda times u. So you plug this value in for Planck's constant, you plug this value in for the velocity, and then the wavelength, you just need to take this value and convert it to meters, and then plug it in down here, plug it in, solve, and you should end up getting a mass of 2.12 times 10 to the negative 25th grams. Now, when you initially solved for this, you would have gotten an answer in kilograms, so you would have gotten 2.12 times 10 to the negative 28th kilograms. When converted to grams, you get 2.12 times 10 to the negative 25th. So C is the correct answer. All right, let's briefly talk about electron interference patterns. So at the end of the first section, we talked about interference patterns. So now electrons, they too have interference patterns, because electrons, they are so small that we notice the wave-particle duality much more than we do with, macroscopic scale objects. So we have an electron source. We're firing these electron sources at a wall here that has two slits in it, and so we begin to see interference patterns on the other side. So this again is because of wave-particle duality. With a few electrons, so a few individual electrons, you can see the individuality a bit more. But if you have many electrons, so you fire thousands, millions of electrons at a board here, you begin to notice these interference patterns forms, so the wave-like patterns begin to emerge. Alright, now let's dive into some quantum mechanics. So here we are going to talk about the Heisenberg uncertainty principle. So this states that it is impossible to know simultaneously both the momentum, represented with the variable p, and the position, x, of a particle with certainty. So what this essentially means is we can't know exactly where an electron is at any given time. We can only know where it is likely to be found. So electrons are so small, they have quantum-like properties. And so because they are so small, we cannot know both their momentum and their position at the same time. We can only know one or the other. So really, we can only know where it is likely to be found. So the region where an electron is likely to be found is called an orbital. So orbitals are essentially clouds of electrons. So we're moving past that more rigid ring-like structure from the Bohr model, and we are thinking of electrons. They are positioned in orbitals, and these orbitals are essentially their probability clouds, or they're kind of like heat maps. They tell you where an electron is likely to be, so we know an electron is likely somewhere in these orbitals, but we don't know exactly where in the orbital it is. Now, each orbital can hold up to 2 electrons. So the Schrödinger equation, this mathematically describes the orbitals in a hydrogen in a hydrogen atom. So quantum numbers, what we can derive from this are quantum numbers. And so quantum numbers in this equation tell us the size, the shape, and the orientation of the orbital each electron is in. So we have 4 total quantum numbers. So the first 3 quantum numbers coming from the Schrödinger equation, the principal quantum number, the angular momentum quantum number, and the magnetic quantum number. So principal quantum number uses the symbol n. So we are familiar with this from what we were looking at earlier in this chapter. This describes the size and the energy level of the orbital. So if you're in the first energy level, n equals 1. Second energy level, n equals 2. Third energy level, n equals 3, and so on. The second quantum number is the angular momentum quantum number. It is represented with the variable L, and this defines the shape of the orbital. So there are 4 L values you will need to know, and we'll get into them in a few slides here. The third quantum number is the magnetic quantum number. This is m sub L. This describes the orientation in space of the orbital. The final quantum number is the electron spin quantum number, m sub S. This is specific to an electron, and this tells you if an electron is spin up or spin down. And so we are going to use these quantum numbers to define where our electrons are. It's kind of like an address. Electrons have a principal quantum number that tells you the energy, the size / the energy level of the orbital they are in. They have an angular momentum quantum number that tells you the shape of the orbital they are in. They have an m sub L number, which tells you the orientation in space of the orbital, and finally m sub S, which tells you the spin of the electron. So let's dive into these a little more deeply. We're starting with the principal quantum number n. Again, this value of n corresponds to the value of n from Bohr's model of the hydrogen atom. So n equals 1 for the first energy level, n equals 2 for the second, n equals 3 for the third, and so on. So as n increases, we have larger orbitals, and we also have higher energy levels. So larger n values equal larger orbitals and higher energy levels. The allowed values for n are integers starting with 1. So 1, 2, 3, 4, 5, 6, 7, and so on. We really only see up to 7, but in theory it could go higher. So allowed values are integers starting with 1. And you're going to see this term shell. The term shell here refers to collection of orbitals with the same value of n. So all of the orbitals in the first energy level would be referred to as the n equals 1 shell. All of the orbitals in the second energy level would be the n equals 2 shell, and so on. The second quantum number is the angular momentum quantum number, L. Each shape has a particular value of L, and you will need to memorize these values and these orbital designations. L equals 1 corresponds to an s orbital. L equals 0 corresponds to an s orbital. L equals 1 corresponds to a p orbital. L equals 2 corresponds to a d orbital, and L equals 3 corresponds to an f orbital. And so we're going to learn a little more about these orbitals here. Now first, I want to talk about the allowed values. So the rules work a little differently for this second quantum number. The second quantum number relies on the first quantum number. So allowed values of L depend on n. So the allowed values for L range from 0 up to n minus 1. So for example, if n equals 1, the only possible value of L is 0, since L can range from 0 to n minus 1. So if n is 1, the only possible value is 0, which means the only possible orbital is an s orbital. When n equals 2, there are two possible values of L, right? If n equals 2, then L can be 0, or it can be 2 minus 1, which is 1. So when n equals 2, there are two possible values of L, 0 and 1, which means there are s and p orbitals in the second energy level, whereas there is only an s orbital in the first energy level. When n equals 3, there are three possible values, 0, 1, and 2, which corresponds to s, p, and d. So in the third energy level, there are s, p, and d orbitals. And finally, with n equals 4, L can be 0, 1, 2, or 3, meaning all four types of orbitals can be found in the fourth energy level. This other term you may want to know is subshell. So subshell is a collection of orbitals with the same value of n and L. So I could say my n equals 2 shell would refer to both the s and p orbitals. That would be my n equals 2 shell. Whereas I could say I have a 2s subshell. So that specifically just refers to the 2s orbitals, or a 2p subshell, which just specifically refers to the 2p orbitals. Now briefly, looking at the size and nodes of orbitals, and nodes are areas where there is no electron density. Here is our 1s orbital, where this is a 2s orbital, this is a 3s orbital. So you notice that the orbitals get much bigger as n increases, and you also notice that there is a sizable gap. So there's a sizable gap or a node in between each of the orbitals. So between the second and the first, there is this what's called a radial node, this gap where there's no electron density. Between the third and the second, same thing. We get this big node right here. Alright, so let's talk about these orbitals a little more specifically. First, we're starting with an s orbital. S orbitals, they are spherical. So when something is spherical, it has only one possible orientation in space. So there is only a single s orbital in an s subshell. So each energy level, n equals 1, n equals 2, n equals 3, and so on, they each have one s orbital in them, because there is only one way to arrange a sphere in space, right? You can't tilt a sphere along the x or the y or the z axis. It's symmetric in all directions. It's a sphere. So there's only one possible orientation, which means there is only one s orbital in an s subshell. Next are the p orbitals. So p orbitals are dumbbell shaped. They have two lobes. So because they are dumbbell shaped, they have three different orientations. There are px orbitals, there are pz orbitals, and there's py orbitals. So there are three different ways to arrange this shape in space, which means we have three p orbitals in each p subshell. So in the second energy level, there are three p orbitals. In the third energy level, there are three p orbitals. In the fourth, and you get the idea. In each energy level, besides the first, there are three p orbitals. Because of this shape, there are three different ways to arrange it in space. Next are the d orbitals. So most of them are clover shaped. So these 4 are clover-shaped, and this one is a little different. So there are 5 different orientations. There are 5 different orientations here, which means there are 5 d orbitals in each subshell. So in the 3rd energy level, the 4th energy level, and so on, you will find 5 d orbitals. Finally are the f orbitals. So now with the d and the f orbitals, I don't expect you to remember the shapes because they are very complicated. But what I'll say about the f orbitals is most have either 6 or 8 lobes. But what's important is that we've discovered there are 7 different orientations, which means there are 7 f orbitals in each subshell. So in the 4th and 5th energy levels, you would find 7 f orbitals. All right, let's talk about our 3rd quantum number, m sub l. So this refers to the orientation. So each orientation has a corresponding m sub l. So for example, px, py, and pz could correspond to 3 different m sub l values, -1, 0, and +1. So let's connect this all together. The allowed values of m sub l, they depend on l. So just like how the allowed values for l depended upon n, the allowed values for m sub l depend on l, and they range from -l to +l. So if l equals 0, there is only one possible m sub l value, it's 0, which means we have an s orbital. So this makes sense if we think about it, right? If l equals 0, that means we have an s orbital. And if l equals 0, then m sub l can only be 0, so there's only one possible orientation in space. And s orbitals, they're spheres, which only have one possible orientation in space. So it lines up. The m sub l values correspond to the possible orientations in space of that type of orbital. So when l equals 1, the possible m sub l values are -1, 0, and +1. So there are 3 possible m sub l values. Now l equals 1 corresponds to a p orbital. And remember that p orbitals, those were those dumbbell-shaped orbitals that have 3 different orientations in space. So 3 different orientations in space, 3 possible values that correspond to those orbitals, the px, the py, and the pz orbitals. When we get to l equals 2, we have 5 possible m sub l values, -2, -1, 0, 1, and 2. So 5 possible m sub l values, which corresponds to the 5 possible orientations in space of the d orbitals. And then finally, when l equals 3, m sub l has 7 possible values, -3, -2, -1, 0, 1, 2, and 3. 7 possible values, which corresponds to the 7 different orientations in space of those f orbitals. All right, so here, this page summarizes the orbitals. So the energy levels are shown vertically, and then the subshells are horizontally. So I'm not going to go over this, but I recommend checking this out if you're struggling. This kind of summarizes it in a nice, neat way. All right, let's try a knowledge check question. How many orbitals are in a subshell designated by the quantum numbers n equals 4 and l equals 3? All right, the correct answer here is B7. So if L equals 3, this means that M sub L can be -3, -2, -1, 0, 1, 2, and 3. And so we have 7 possible values, which means we have 7 orbitals in that subshell. So B7. All right, another knowledge check question. Which of the following is a legitimate set of 3 quantum numbers for n, l, and m sub l, respectively? All right, the correct answer here is A. A is the only set that follows the rules correctly. If we look at B, so remember that the first value is n, the second value is l, and the third value is n sub l. If we look at B, the issue here is that L is the same as N. And remember, for L, the allowed values are from 0 up to N minus 1. So if N equals 3, the biggest that L can be is 2. So B is incorrect. C, well, N looks good. L looks good, but the problem is with M sub L. So remember, the rule for M sub L is that it can be from -L to +L. If L equals 0, then M sub L has to be 0. That is the only possible value. So C is not a correct set of quantum numbers. And then the same issue comes up here with D, where it shows M sub L having a larger magnitude than L. So D is incorrect as well. A is our answer. All right, let's talk about that last quantum number. It's the easiest of the four. It's the spin quantum number, M sub S. Now remember, each orbital can hold up to 2 electrons. So if we have 2 electrons in the same orbital, where their first 3 quantum numbers are all going to be the same. They'll have the same N, the same L, and the same M sub L. So we need a way to differentiate them, because every quantum number needs every electron needs its own set of quantum numbers, like an address. It gets its own designation. So if the electron is spin up, we say M sub S equals plus 1/2. If we say if the electron is spin down, we say its M sub S value is negative 1/2. So this takes us to what I was just talking about, the Pauli exclusion principle. No 2 electrons can have the exact same set of quantum numbers. Each set of 4 quantum numbers describes 1 electron, just like how each address describes how to find 1 person. Okay, that is the conclusion of section 3.3. I'll see you in the next one for section 3.4, electronic structure of atoms.